Welcome back. We're going to go over Unit 8 of Algebra 2. This is about evaluating logarithms. We're going to cover how to solve a logarithm, what a logarithm is, the parts of it. We're also going to look at the properties of logarithms um, and a little bit about the natural logarithm, which is written ln instead of log. Um, but I would suggest watching some videos on natural logs. I'm just going to explain just very briefly that part. But we're going to start today by looking at how to solve a logarithm. So this here says we have log of uh, it says log 6 216 216, or we can say this is log base 6 216. So the 6 is the base. And this 216, many times you'll see it in parentheses. That's called the argument. And then this x here, if we rewrite this as an exponent, this is actually 6 to the x equals the argument 216. And we're going to start today by doing some guess and check with these. But then we're going to look at how we can take the log of both sides in order to get an answer faster and in order to get an answer for some of these tougher ones where it would be almost impossible to do guess and check. Now, whenever I'm trying to teach students how to write it like this, I think about it in terms of, or I call it anyway, I call it the snail rule. So we start at the base, we wrap around the equal sign, and then it kind of snails in to the 216. That's just what I call it. It's not called that anywhere if you look it up, but that's just what I call it because it kind of looks like a snail shell, like how a snail shell wraps around. And that just helps me to remember how to do logs every time. So I call it the snail rule. Um, so now we're going to do some guess and check for this. So 6 to the power of what is 216? Well, we know 6 squared is 36. So let's try 6 cubed and maybe we'll get lucky. And it is. So x equals 3 for this. So that's how we can evaluate logarithms. We set the equals just equal to x, and then we write it in the snail rule, and we try some guess and check. I'm just going to write this one out because it's probably going to be faster than just copying it. So log base 3 of 9 is equal to x. Do the same thing. Do the snail rule. 3 to the x is equal to 9. And I think we can see very clearly x is equal to 2. 3 squared is 9. Okay, so that's some easy evaluating logarithms problems. Now we're going to go to some tougher ones where we have to use one of the rules of logs, which is taking the log of both sides. And I'm just going to change my screen share. I just want to double check everything's correct on my end here. Just want to make sure I'm sharing the right screen. Okay. All right. So, oops. Okay. So here is the next problem. So the next problem says log base 25 1/5. So if we set this equal to x, we can still do the snail rule. 25 to the x equals 1/5. But this becomes a lot more difficult to check with the guess and check method. Now, there's a couple different ways to do this. I'm just going to show you the way that I would solve this by doing what's called taking the log of both sides. So if we take the log of both sides, that's kind of like in terms of algebra, we can divide by the same amount on both sides. We can multiply by the same amount on both sides. We can add by the same amount on both sides, subtract by the same amount. So that keeps the equation true if we do the same operation on both sides. We can also do what's called taking the log of both sides. So we can write this as log 25 to the x is equal to log 1/5. Now, another one of our rules or properties of exponents is called the power rule. And the power rule says if we have the log of something and it's raised to a power, we bring the power to the front. So we write it x log 25 equals log 1/5. And that's called the power rule. And this is just saying now x times log 25 equals log 1/5. You might be wondering, hey, we had this base 25 on this problem. The last problem we had base 3. Problem before that, the first one we had base 6. You might be wondering, where's the base? Where did the base go on this? And if you notice that, that's a really good observation. Anytime we don't have a base on a log, it is implied that it's base 10. So we don't write the base 10. I'm just writing that in right now. And the reason that that is because we can cancel algebraically if we can get things like log base 10 of 10. If we set that equal to x and do the snail rule, then we get 10 to the x is equal to 10. And that's a really easy answer. We get x equals 1 for that. So log base 10 of 10 is 1. So anytime we get log base 10 of 10, we can just cancel it out if we're multiplying by log base 10 of 10. And so that's why log 10 is implied. Okay, kind of a side note there. Let's get back to this power rule question. It's going to erase this. So we bring the x to the front, and that's called the power rule. Now our very last step in terms of solving algebraically is we divide by log 25 on both sides. And here you might want to use the Desmos scientific calculator. I think that that's probably the best way to solve this. If you go to desmos.com/scientific, you can just type this in now, log 1/5 and log 25. Now you can only type in log base 10 in the calculator, but this is in log base 10, it's just log. So you can use a calculator for this. And if you type that in your calculator, you will get exactly an answer of negative 0.5 or negative 1/2. Okay, so that's how to solve some of these more challenging problems. Let's see if maybe we can go to another one. Next one is, I'll just copy this next one, I guess. This one says log base 27, 9 equals some amount. So we'll start by setting it equal to x. Do the snail rule, 27 to the x is equal to 9, is equal to the argument. Now we can take the log of both sides. So we get log 27 to the x equals log 9. We're going to use the power rule. We get x times log 27, or just we read it x log 27 equals log 9. And then we can divide. And there is another way we can solve this, but I like to teach this way because this is what we're going to use later when we're solving properties of logarithms. equations. So this is, I think, good practice to start with, in my opinion. So again, those cancel out just like the last time. And then we're just going to type this in our calculator. So again, desmos.com/scientific. Log 9 over log 27. And we get 2/3. So again, this is saying 27 to the 2/3 is equal to 9. So you can easily check that on your calculator if you have to. So you can type that. In fact, I'm going to double check. 27 to the power of shift 6 is how you do the exponent if you're typing in your calculator. Then when you put the exponent in as a fraction, just make sure to write it as write it with parentheses. And I didn't share my screen for that, but that's just how you would do that on the calculator. Okay, so that's evaluating advanced logarithms. The next part is getting us to think about how do we write an exponential equation as a log, and how do we write a log as an exponential equation? We already did this one of the ways. We've got to work backwards for the other one of the ways. So for this one, the first part, it has everything written as an exponent and it wants us to write it as a log. That I think is a little bit tougher. It's like doing the opposite of what we've been doing so far with the snail rule. Let's start with this bottom one. These are two different equations. They do not match at all. They're two different equations. But let's start with the bottom one. This should be review because we've done this with the snail rule already. The base is 9. We're going to wrap around to the argument, or excuse me, the answer, and then back to the argument using the snail rule. So this is 9 to the negative 1/2 is equal to 1/3. And this should be a true statement when we get a final answer here. So let's double check that. 9 to the negative 1/2. And just type that in your calculator, and you should get 1/3. And so that's how you can check to make sure that you did this correctly. So instead of it saying it's equal to x, it's actually giving us this value to plug in for our exponent, or what we did earlier for x. So now we have to go the other direction with this. And I always thought this was difficult. I still think it is a little bit difficult because normally we're used to seeing logs first and then we write it as an exponent, but sometimes you might have to go the other direction. So this 1/6 is by itself, that is going to be the argument of our logarithm. So far we have log 1/6 is equal to, and now we have to figure out what this is saying. So the base of our exponent is the base of our logarithm. That's a really easy one to remember. The base is the base. So this is called the exponential base. This is called the logarithmic base. And so now this is log base 6 of 1/6, or log base 6 1/6 is equal to, and then the only number we have left over is the negative 1. So when we're writing a log out, writing a logarithm, what it's equal to is equal to the exponent of the exponential form. The argument is by itself on one side. The base is the base. And so that's how you can match up those three different parts. Okay, so that's rewriting them in the other direction. Let me see if there's might be another. Okay, so some of these they might be telling us in a table. Let me see here. Just a second. Let me just double check that everything is okay. Okay. I think I know I'm gonna explain this to you now. So sometimes they tell us these values that are in a table, and what it wants us to notice from this problem is that if we have an exponential function written as an exponent, the inverse function is the logarithm. So we'll take a look at this here. It says y is 6, what is x when y is 6? Well, we're going to look at the logarithmic function and we're going to figure out, well, what happens when x is 6? What is y? It's 1.631. And then the inverse of that is for to find out this x value for the logarithmic function, we look at the y value for the exponential function. Or excuse me, we look at the x value for the exponential function. So let me see here. No, excuse me, we look at the y value. I'm sorry. So we're switching the x's and the y's. I saw two twos in this table, so I got a little bit mixed up there. But notice this first column, the values are swapped. It skips the 3 and the 1 on the second column. But if you look at this column, these values are swapped. And that's just called the inverse. So this one, there's going to be a 9 for this one. And I don't I don't think this is incredibly important to know. I mean, it is important to know, but when we look at this graphically, I think it makes a little more sense when we look at things graphically. Okay. Actually, let's do one on the graph. So here's one with it says it gives us these points, and we have to figure out where do these points go if we're thinking about here's what they gave us on the exponential graph. Where does our logarithmic points go? Where did those points go? And again, it's just the inverse. So it's the opposite of. So we have xy for these green points here. So 0, 1 is one of our points. 1, 3 is another point. 2, 9 is another point. And it looks like 327 is another point. And so just like we did on the table, we're just going to write the inverse of it. So this is y equals b to the x. Those are the points that we got for that. And if we want to find y equals log base b to the x, then we just write the inverse. So this is going to be 1, 0, 3, 1, 9, 2, 27, 3. And you would plot those points on the graph. So let's do that really quick. So 1, 0, 3, 1, 9, 2, and 27, 3. And so if you notice, it's symmetric across that line. Okay. So that's what those look like graphically. All right, the last section for today for this is all for quiz 1 on the property of logarithms. We're going to talk about properties of logarithms. So here are all the properties of logarithms. And you might want to pause the video and take a screenshot of this. Um, we have the product rule, which says that when we have the product of two items within the argument with the same base, we can then rewrite the logarithm as addition. So we can write it as two separate logs being added together. And that's very similar to how we add the exponents with our properties of exponents when we have the same base. That's essentially the same idea. For the quotient rule, we have log base A is the argument x divided by y. So when we have the argument being divided, we can write them as two separate logs which are being subtracted. This is only if we rewrite them with the same base. So A and A never changed. The power rule, we went over that one already. If we have an exponent, we just bring that exponent to the front, and then it's multiplied by the log. And then the change of base rule, that's actually going to be, I think, in our next quiz, but we can take a look at it real quick here. The change of base rule says if we had log a to the x and this was not a 10 and we needed to use a calculator for some reason, we could find the answer with the change of base rule by rewriting it in terms of base 10. So this log a, let's say it's like log base 3 of, and then we have a number here. We could just write this now as log base 10 and log base 10. We'll go over the change of base rule in the next video. And then the equality rule, this just says if the bases are the same and they equal each other, that the arguments also, of course, have to be the same. That's the equality. Okay, so if the change of base rule, I just very briefly mentioned what it is. We're going to go over it in more detail, so don't worry too much about that right now. We're going to start, though, with this first question, and it says two logs are being subtracted. They both have a base 10, so they have the same base. So that means we can use the quotient rule and rewrite this as log of 15 over 3. And we can simplify that. 15 over 3 is 5. So that would be log 5. Okay, let's try a couple more of these. This one looks like we're going to be using this next one. Let me erase this. It says 3 log 5. This is also base 10. It's just implied. So now we are going to use the power rule, but we're going to use it the other way around. We're going to rewrite it as, it looks like they want us to just rewrite it like this, like log 5 to the power of 3. So some of these, they want you to go forward. Some of them, they want you to go backward. Let me make sure I put the exponent in the right spot. So that's not technically correct the way that I wrote that. Let me go back. So this is actually 5 to the power of 3 like this. So this becomes log 125. Okay. So let's see if we enter the answer in just with 5 cubed like that, if it lets us. No. So we have to expand it like 125. That's why it said it was the answer. So just, I guess, as a good habit, let's keep the exponents inside the parentheses. That would probably just be a good habit. So we'll write 125. We'll try one more of these after this one. Okay, this next one's a plus. It says rewrite this log in the form of a single logarithm, log C, that's what that means. Let's write it in terms of one logarithm. This is the product rule. That means we're going to multiply the arguments. and combine this into one just log base 10, and that would just be 5 times 2. And again, if you wrote 5 times 2 for your answer, it's probably going to say it's the wrong answer if you're typing it in. So this is log base 10, or excuse me, log 10. And interestingly enough, this is base 10 also, and that is equal to 1. But it wanted us to write our answer in terms of a log, so log 10 is what you would enter in there. Okay, so that is everything for quiz 1. Just kind of a side note, though. For some of these videos, they have to do with E. So you're gonna use E sometimes. And I just want to show you that log base 10 of 10, we just went over log base 10 of 10 is equal to 1. We have what's called the natural log, ln. And whenever we see a letter E, that is equal to an actual value. If you type E in your calculator, it's going to give you a value that goes on forever. And it's equal to about 2.718. But we can find the log of E very, very easily by using the natural log, which a natural log is like a logarithm with base E. And so ln E, E, well, it's also equal to 1 because E to the 1 is equal to E. So E is approximately equal to 2.718. Okay, so we use E for a lot of financial problems, trying to determine what the best outputs would be for certain financial situations where we're making investments. So that's usually where we use the letter E from. But I just wanted you to be aware of of these two rules here, because we can cancel out terms and equations by getting rid of the logs and replacing them with 1 whenever possible. Okay, so that's everything for quiz 1 on the introduction to logarithms.